Say, you want me to
I'll do a quick recap of previous class, but let me first add the note here. Today we'll be doing something called the Hall probe. It's very important like a topic, and there are a couple of derivations of it. So if you have like school exams coming up on this topic, it's almost like guaranteed you'll get a Hall probe question because recent syllabus they made it more complicated, and there's plenty of questions that came recently. Okay, so again we'll just do a recap of this and then work on the Hall probe.
What's the equations for the coming test? For the coming test, like past the chapter or something, 40 equations.
40? Should be more. Yeah. What equations did you consider? Like all of them or just the final derivations? Yes, so there's some intermediate equations. So for example, a simple harmonic motion, right? The velocity, how many equations are there? 3.
X square x square.
Okay, so yeah, that's right, that's 3. So if you have counted all of those, it should be around, I think 50 plus. But to which chapter did you come? Magnetism or? That'll be good. Overall, you have around 75 equations. No. It's still capacitors. No. I was planning to include the motor effect. Okay. So yes, capacitors. Okay, so when the particle enters at an angle, there are components that act perpendicular to the plane, and this results in the circular motion. Component that is parallel causes the particle to move downwards. Hence, it undergoes a helix pattern, the one you can see on the right. Okay. So yeah, this is the one. I think you messaged me about this in the class, right? I don't have a recording of that, but I just have the notes, so I'll just update the notes. I'll be discussing that right now. Right, so this is the spiral in bits that you see. Okay. I'll just do a quick recap of everything because we need all of these for today's class. So let's just go through them again. So yeah, the chapter that we started last class, it's like a core topic. Very often questions come from here. Charges in magnetic field. Okay, so what does this chapter deal with? It deals with, as the name suggests, what happens when charges enter a magnetic field. So as your charge enters a magnetic field, it turns out, according to motor effect or Fleming's left-hand rule, if your charge is going this way and your magnetic flux is into the page, based on Fleming's left-hand rule, there must be a force acting that way. And as a consequence, what happens? The particle moves that way. But interestingly, as the particle starts to change direction, the force also keeps changing direction and retains what direction to the velocity all the time? Perpendicular direction. So it means that your velocity, velocity our force key direction act perpendicular. And that is actually a requirement for what? Circular motion. As a result, your particle will start to go in a spiral. And that's what happens. So whenever a charge is moving a magnetic field, they experience force and they go in a spiral. Now, this is the one I said. If it enters at an angle, you have one component that's perpendicular, one component that's parallel. The perpendicular component will make it go in spiral, and the parallel component will make it go down. As a consequence, it'll start to go down like a spiral staircase. Okay, so that's like an extreme version of it. And we saw that if you want to find the force, the formula is this: F equals to BQV sine theta. Very important at the equation. F is the electromagnetic force, B is the magnetic flux density, and Q is the charge of your particle. V here is the velocity. So if you see the velocity is 0, what is the force? 0, which means that the force can only act on a what charge? Moving charge. And that's the definition of electromagnetic field, that it is a force exerted on a moving charge. And sine theta is the angle between your charge and the magnetic field. So what if your particle is going like this and the magnetic field is like that? They're not perpendicular, right? So you need to find the component and then you can apply. So a component very project, no, as a placeholder, sine theta dawa. It could be cos theta as well, but the idea is that you need to incorporate what into your calculation, the angle, the component. Okay, so yeah, that is the formula. F equals to BQV sine theta. Now, just like every other circular motion that we have seen, your centripetal force is provided by some other force. So in this particular scenario, who provides your centripetal force? The magnetic force, the electromagnetic force. And once you equate them, you get this equation out there. If there's one equation I would suggest examiner make sure to remember, this is probably it. Okay, because this is very handy in multiple places. So R equals to mv divided by bq. M is the mass, v is the velocity, B is the magnetic flux density, Q is the charge. So once you incorporate all of them together, you'll have the radius that the particle takes. And I think we did a simulation, like, you can vary the radius, make it tighter, make it loose. Right, and we also saw something else here, which is if you take the other equation and try to find the time the particle takes, right? The time the particle takes is independent of a very important quantity here. What is that? Radius. So radius cancel out to the j, which means if your particle keeps spiraling inwards like that, the time it takes to make one circle will always be what? Same. Okay, so even if it spirals outwards or spirals inwards, the change in radius doesn't really have an impact on the time. Okay, so why is the change in radius not having any impact on the time? Well, I mean, mathematically it shows that the radius cancels out. We get the math logic, but what's the subjective version of it? Like, why is it that radius doesn't have a role to play on the time period?
Speed of circles increasing on the radius.
Right. So that's actually correct. So as the particle goes further and further, obviously radius increases, but what also increases? Speed, because there's a formula, V equals to omega r. So that's why it turns out that the bigger the radius, the faster your particle. So eventually, what time does it keep taking? The same time. Okay. So if you want to change time, by the way, you have to change the B, the Q, or the M. So one of these things. Okay. So yeah, that's what we saw till last class. Before I move on, I'm going to do something called the Hall probe. It's a very interesting topic, also a little challenging. I want you to try out one of these maths here. It's this classical question, which is, what is the ratio of the radius taken by an alpha particle to the radius of a beta particle? So you enter an alpha and beta particle into the field, right? How does their radius compare? So let's look into that. It's an example, it's a math, so you have to try it out. There you go. An alpha and beta particle enters the field at same speed. The ratio that you need to find is, what's the ratio of the alpha to beta particle? I'll give you like a diagram here for context. So I've given all the values out there. Examine, they will not give you the values because they're expecting to know alpha and beta is what composition. So you know alpha, right? 4 and 2. And what is beta? 1 and 0. 0 and -1. No, that's the symbol for beta particle. But like, what's the mass of? Or what is the beta particle? An electron. So it's 1/1836, the mass of a proton. But yeah, তোমরা যেটা বলছো, that's not wrong. That's the notation বলা হয়, 0 and -1. Right, so you have your magnetic field here. Listen carefully what's going on here. You have your alpha particle entered the field from this side, and it's entering like that. So there's a beta particle also entering like that. You need to find out what kind of path do they take in the magnetic field. So you need to find the ratio of their radii. Okay, so alpha is to beta. So if 1 is to 1 detached, okay? So the mass of alpha is provided here, 4 into 1.6 into 10 to the minus 27. Mass of beta is provided. Charge of alpha is provided. Charge of beta is provided. It's a 3-mark question. It's right, bro. The equation that you need to solve this, or the equations are provided in the yellow boxes here. So this is one of them. And maybe this here. Right. So Tajibar, I just want to be done with this, and I want to start Hall probe. Question so I think I told you maybe that the alpha particle will enter and bend one way. Can you tell me which way does the alpha particle bend here? Let's start with that first. How do you find that? Clemens left-hand rule. So FBI, I represents what? The direction in which the charged particle enters the field. Always remember that, okay? So it enters the field that way. X is what? Magnetic field. Which way is that? Into the page. So as into the page. Which way is your thumb pointed? Upwards. So you find that the alpha particle goes upwards like that. So, you know, it'll be part of an arc. Like it's a larger circular arc apart. A beta particle will go which way? Downwards, right? So it's going to go downwards. But will it follow the same path, or will their radius be different? So it should be different, right? That's something you know from your O levels, that they're a little different, right? So now find the math and tell me how different are they. Could anyone find the ratio?
3,500.
3,500 is to 1. Yeah, also, but you should ignore the negative sign. It's a radius. So just the magnitude of the charge would be needed. Right, so that's the answer. Are you guys trying to solve it or I'm going to very sad? Okay, so let's see how to solve this. So these questions of ratio, they're best approached if you know which equation to use. And which equation do we have here that has radius in it? Yep, R equals mv divided by bq. So if I consider radius of alpha here, so this is radius of alpha, that is supposed to be equal to mass of alpha times velocity of alpha divided by the magnetic flux density that alpha experiences times the charge that alpha has, right? And if I want to find the radius of beta particle, it'll be exactly the same thing, mass of beta, velocity of beta divided by flux of beta times charge of beta. And what are we trying to do here? We're trying to find the ratio of R alpha by R beta, right? Because see, it says alpha is to beta. So what are you going to do right now? Just divide these two. So therefore, to get the answer, what we do is R alpha divided by R beta. And once you divide these two, you'll find that things simplify. I'll show you how. So this goes here, divided by that goes there, and then divided by a line here. So once you do that, what will happen is the thing that you see at the bottom will become like a reciprocal, ulta jabe, right? So this is going to be equal to, sorry. Do you follow what I'm doing? I just, I'm dividing the two expressions that we have. So because this is 1 by something, it will flip over. And what do we have as a consequence of that? So you'll have this into কি হবে বলো তো? Basically এটা উল্টা যাবে। হ্যাঁ, right. একটু কি বুঝছো তোমরা what I did here? আচ্ছা, এরপর it's very easy. It's like I think super easy. What you need to do is just cancel things out, and you'll find a lot of things cancel out. So it says in the question that they enter at what speed? Same speed, right? So right away the velocity is not of any consequence. They're passing through what magnetic field? Same magnetic field, so the B also cancels out. So eventually this is a reminder of something that we have seen before, that particles in any field, right, if there's electric field or magnetic field, they rely on two factors for their deflection. It's called a mass to charge ratio. Do you remember in the electric field chapter that only the mass was not the factor, also the charge was a factor? You'll see it comes back again. So always remember that whenever you are dealing with your charges, the mass is also a factor, because the mass does play an important role here. Are you clear about that? So এখন কি করব আমরা, just we'll just replace the value of their masses. So what's the mass of alpha? For U, আমি এটা অন্যভাবে একটু করি because I want to teach you something. Do you know what U is? Yeah, it's unified mass, atomic mass unit, right? So atomic mass unit বলা হয়, it's 1.67 × 10⁻27, right? And do you know what the mass of beta particle is in terms of U? No. Yes, U divided by 1836. Now, এটা যদি তোমাদের কাছে confusion মনে হয়, just use the actual value. There's nothing wrong there. But I'm showing this because eventually exam U they করে অনেক সময় marks give away. Into what's the charge of beta particle? 1. What is the charge of alpha particle? 2. like কিন্তু 2e থাকে এখানে, e গুলো কি করে দেই আমরা, cancel করে দেই, so u গুলো cancel হয়ে যায়. So eventually you get what? 4 divided by 1 divided by 1836 into half. এটা ক্যালকুলেটর বসালে you're supposed to get 3672, right? 3672 is to 1. তুমি যদি উপরের ভ্যালুগুলো ইউজ করে থাকো তাহলে তোমাদের অ্যান্সারটা একটু ডিফারেন্ট আসবে 3, 5, 1, 2 or something. Yeah, so essentially the thing that I want to show you here, the reason I am doing this math is that the radius of an alpha particle to the radius of a beta particle is drastically different. 3672 is to 1. মানে হচ্ছে for every centimeter that your beta particle spirals, your alpha particle will spiral how much? 3672 centimeters. What's the real life implication of that? So the real life implication হচ্ছে if an alpha particle is in your chamber and a beta particle is in your chamber, you will not be able to see both of them spiral. I'll explain what I mean by that. So if your beta particle spirals in this chamber, it means that the alpha particle will have to spiral with such a large radius that in your screen, the amount that you have, the alpha particle will almost go straight through. Why is that so? So to give you a better idea of how scales matter here, this is like the alpha particle's radius. Let's assume that to be 3 meters. The beta particle radius is going to be 0.1 nanometer. No, 1 centimeter. Guess correctly, the number does it or this is 1 centimeter. So 1 centimeter judi hoy, the other one is going to be 3 meters. So how does that look like in real life? It means the beta particle will spiral here within the tip of my fingers, and the alpha particle will take how much to spiral? The entire room. So it will just go in a big circle in the entire room. So if you look at a point here and you try to see this spiral, so let's say I make this particle spiral here, okay? See what I'm going to do right now. So I'm going to make this a very large circle and make it spiral. So you'll find that the bigger the circle becomes, the flatter the part would become within the field. So do you see that the red line looks almost going straight through? Now this is not even the right scale, it is even bigger. So eventually you'll see that the alpha particle almost goes straight through. The key word here is almost, okay? So you'll show some amount of what here? Curvature, right? But then again, if you want to show the alpha bend on your screen, right? Beta key hobe. Yeah, it'll be like a dot. You wouldn't be able to see it because you have shown the alpha bend, so the beta can't be seen on the screen. So either ways, both of them can't spiral equally on the same screen. That's the point. Okay. All right, so let's move on. আমাদের হচ্ছে কি করতে হবে এখন? So I already mentioned it multiple times today. So এখন শুরু করি এটা. It's a device that we're going to learn, a very handy device. It's called the Hall probe. So the Hall probe is a device that we designed to find the strength of magnetic flux density. So it's called the Hall probe. You can add it to page 123 pashe. So just screen it দেখো আমি জিনিসটা বুঝাই কিছু লেখো না it's technically too challenging. So what is Hall probe? So Hall probe is a device that we use to find magnetic flux density. So prior to this device we didn't really have any device to find magnetic flux density. But how do you find the strength of a magnet? That's my question. So let's say I give you a magnet and ask you how strong is this, right? What's the way that an O-level student will figure that out? What would you do if I give you a magnet? Yeah, just see how many pins it can raise. If one magnet picks up 10 pins, another magnet picks up 20 of those pins, the other one is stronger, right? But there's no number for it. It's just a subjective analysis, right? There's another way you can do this. You can place iron filings around it, and what will it produce? A pattern, right? And the pattern, if you see the lines are very closely packed, what does it show you? Strong. But again, it's a very subjective value, right? So how can we get a number out of it? How can we quantify this? So quantify করার জন্য there is a number that tells us how strong a field is, which you guys should know. What is it? No. Yes, magnetic flux density. So the strength of a magnet is based on the magnetic flux density or magnetic field strength. Basically, what is it? B. So you need to know the B value here. The Tesla, 0.5 Tesla, 1 Tesla, 2 Tesla, these values, right? How can you find it? So we actually went through a scenario where we found it. Do you remember which one? Which one? Where you can, sorry? Right, very good. So we have found that you can actually use this formula F equals to BIL sin theta. এখান থেকে B কে subject করলে F divided by IL করে বের করতে পারো. And this is actually a proper way, and this is an acceptable way. But the problem is, it's a very restricted way. So you need to take your magnet and then place a wire through it, place current through it, and see how much the wire forces the magnet down, and then you know what the strength of a magnet is. Now, let's say you're out there working with a magnet, a random magnet hanging from the ceiling, right? How do you do that? Right? So we needed a device, like you just hold up to your magnet and it tells you what the reading is. So what you know, we came up with this Hall probe. You get my point? So the thing is that how can you find the magnetic flux density? This is possible. This is completely fine. In fact, this is one of the ways to define magnetic flux density. Magnetic flux density is what? The force exerted per unit length when a unit amount of current passes through it, right? But how can we make a device like an ammeter or voltmeter? I mean, and it tells me what the strength is. So we have the Hall probe. Now, before I start designing the Hall probe, I have to give you a disclaimer. You make the Hall probe. You can't buy it. Okay, so whenever you want to find the magnetic flux density, you have to first design it yourself. There's no standard thing that you can buy anywhere. Okay, so how do you design one of these things? So what we're going to do right now is set up a magnetic field first. So you take a battery like that, and we have a magnetic field here. Let me bring one. So this magnetic field that you see here is into the page. I want to find the strength of this. That's our plan for today. Okay, I want to find the strength of this. So I'm going to get a corbo. We will take a wire like this from a battery, and we'll pass the wire into the magnetic field like this. And then obviously we'll have current passing through it. Can you tell me which way will the wire experience force because of the current in this wire? So this is plus, this is minus. Current যাচ্ছে হচ্ছে এভাবে. Can you tell me which way would the force be? FBI, right? Current is upwards. Magnetic flux is into the page, so it's to the left. Tomother left, right? So the left দিকে force হবে. Do you understand? So this wire is supposed to move to the left. But what we'll do is we'll make a modification. We will cut off the wire at this location and place a specially designed wire here. This wire is of a certain thickness, okay, an appreciable thickness. It's not a very thin wire, okay? And it also has a very good amount of width and a very appreciable amount of thickness as well. So it looks something like this. It's like a block, okay? So you take this wire and you place it like this. The reason why we do this is we don't want the wire to move. Except because if the wire is very light, wire is short. So we don't want that to happen. We allow it to keep the wire that we place here. We keep it like this, and current will pass through it. And yes, force will be on that side. But then we do something, which is we take a voltmeter and we connect the voltmeter across the wire like that. Do you understand how I've connected the voltmeter? Huh? Not inside the block, on the sides. So if you think of the wire to be this, okay, it's like the diagram over there. I connect the voltmeter on this side and that side, on the sides, because I want to find the watt between the two sides, potential difference. Okay, so we take these two wires like this and we place a voltmeter here, and the voltmeter that you place here is supposed to be a very sensitive voltmeter, which is typically millivolt. So why? Because the voltage is going to be very small, if there is any, right? Now, once you allow current to pass through this and it goes through there, surprisingly, we see that there's a voltage reading here. The question is, why is there a voltage reading? That's the first theory question you get. That why is there a voltage across the wire? Because typically voltage will be across these parts of the wire, and that's called potential difference, as you know. And by the way, if I connected my voltmeter like that, I would get a voltage, and that voltage would be what? The battery voltage, because it's just the one resistor there. But what happens when you connect it sideways? So typically nothing happens, but if it's in a magnetic field, something happens. So the question is, what happens and why is there a voltage? So so far what I did, I took a wire, I placed in the magnetic field, I connected the voltmeter sideways, and now there's a voltage out there, which is not normal, by the way, but magnetic field it happens. So the reason why it happened is because if we dig deep inside the wire, the one that's here, key hoy to the key. So inside this wire, there are electrons moving, right? And the electrons are moving from which side to which side? Can you tell me which way the electrons moving in the wire? Left to right. Why would you say that? It's like a circuit. My question is, I'll give them names. So X and Y. Achha, so which way is current flowing? So yeah, this is X here and this is Y there. So yeah, current goes from X to Y. Which way electrons move? Okay, yes, very good. So now my question for you is that the electrons are moving like this and there's a magnetic field across them. What will the electrons start to do? They'll experience a force, right? Can you tell me which way will the electrons experience force? So FBI once again, right? But we will assume the electrons to be positive charge. So they're going downwards. Magnetic flux is into the page, right? So if the electrons are supposed to move downwards, positive charge, and magnetic flux is into the page, the force should have been this side. But which way is the force acting though? The other way, because the electrons are opposite, right? So you'll find that, what I said, মানে তোমার ইলেকট্রন যদি এদিকে এন্টার করে, the direction of electron কে positive যদি আমি নেই, positive consider great charge, and my magnetic flux is into the page, you'll find that they're supposed to go that way. That would have happened if the electron was what charge? Yeah, but what is the electron's charge? Negative. So it goes the other way, right? So you start to see a stream of electrons here. There's a stream of electrons entering, and these electrons, they're slowly moving which way? To this side. So they're getting deflected to that side. And this particular side of your wire is now having a lot of what show up? Electrons. And as the electrons move this way, they're moving from which side? The other side, right? So this other side has now fewer what compared to before? Electrons. So the other side will start to become what charge? Positively charged. So this side will have a bit of positive charge on that side. Do you understand why the positive charges are there? Because the magnetic field is pushing all the electrons to the left. So therefore, what's left behind? Positive charges. So you have your negative charge on this side, and you have your positive charge on that side. Isn't that the perfect requirement for an electric field? That there are like opposite charges out there. And once you take a voltmeter and you connect the voltmeter across these two, the voltmeter will find the watt between the two sides, the potential difference. And that is the reason you have a voltage here. Now, why do the electrons move to the left? If you use Fleming's left-hand rule, you'll find that the electrons will bend this way. So you first assume the electrons to be positively charged. You'll find that they go this way, but electrons are not positive, so they're negative, so they go that way. Now, what's in it for us? We just deflected electrons, right? Turns out the amount of deflection the electrons undergo is directly proportional, not just proportional, directly proportional to what? The magnetic field strength. Okay, so a magnetic field strength যত strong হবে তত বেশি কি deflect করবে? Electrons deflect করবে। আর যত বেশি electron deflect করবে তত বেশি কি পাবো? Potential difference. And finally, we now find out that this voltage that you get here is actually a proper representation of what? B. So আমরা এই voltageটা দিয়ে B বের করতে পারবো। But there is a small step here, and this is paper 5 question, খুব common. Is the voltmeter reading the value for B? No, it is just proportional to B, right? Then how do I get B? Do you get my question? I mean, I have a voltage 2.1 millivolt, right? Does that mean it's 2.1 millitesla? No, of course not. So how do I get the value of B? Yes, you're actually right, but it's a little more advanced, the one you're saying. I'm looking for a simpler answer. You're going for the derivation for that value. And that's how we derive it. I'll get to that later on. But my question is that, I've given you this wire. There's a voltage of 2.1 millivolt, and there's a magnetic field here. How do I find the value of the magnetic field? Because I just now have the voltage, right? And let's say we haven't discovered the formula yet. What can we do? In a practical point of view. It's a very common practical approach, but I think just say naturally আসে না to students. No. Anytime you have something that you know this is proportional to that, and you know one of the values here, how do you find the other value? Very close. Teacher একটা repeat করে constant বের করবা. Plot a graph. But it's a graph of many voltages versus many unknown B's. How do you find the unknown B's? মানে graph যদি আমি plot করি কি হবে? 2.1, there's a B. B মানে magnetic flux density. 4.7, there's another value of B. কোনো B value তো জানি না. So the thing, there's a very nice name for this process, and the name just suffices in your example. We calibrate it. So what's calibration? We do this experiment in a magnetic field strength that we know. So you can buy magnets. Magnet it's 20 millitesla. Place it here and see 20 millitesla put to voltage there. Which এটা ছিল তো না আমরা তো FRI and L বের করতে পারি no that's what we're finding, right? So anyways 20 millitesla is possible, not in this case, but yeah, possible. So the process is called calibration. So calibration ki kora hoy, you take a known value and let's say now you find that 20 millitesla is 2.1. If it shows 4.2, what is it? If 20 millitesla gives you 2.1 millivolts, if it shows 4.1 millivolts, right, how much should they do? 40, because it's directly proportional. It's a straight line passing to the origin, right? So I'm really actor link বের করতে পারি, wouldn't all of them lie on that same line? So that's how we find it. The process is called calibration. Are you okay with that calibration? That will derive. Okay, so there's another way here. If there's no current or there's no magnetic flux, right? What's the voltage? So it must be straight line passing to the origin. At least we know it's passing to the origin, maybe not straight line. The equation later reveals it's a straight line. At point, if you do this, let's say you randomly have a magnetic field here. It's খুব important to carefully know. There's a magnetic field here. I take my Hall probe. I think I understand Hall probes very well. I place it there, and I get a wrong reading. মানে আমি যে রিডিংটা পাচ্ছি and যে রিডিংটা ওরা বলতেছে they don't match. What have I done wrong? So এটা হচ্ছে paper 5A first question যেটা থাকে the planning. It's anytime there's magnetic flux density, this is going to be part of your answer. মানে they'll ask this question, which is you place your Hall probe in a magnetic flux density and you get a value, let's say 25. But তুমি পরে check করে দেখলে it's not 25, it's actually different. But you did everything right from your point of view. What might have gone wrong? Yes, very good. Okay, so it turns out this will only work if the magnetic flux density and the current happen to be what to each other. How do you know? There's no magnetic field lines that you can see. So how do you know? Yes, it's actually what you do. So you take the block, right, and you keep it rotating in different orientations until the value becomes what? Maximum. That's when you're perpendicular. So to me, rotate korte korte ekta point dekbe 0 hoye jay. That means you're what to the field? Parallel. And then you start to slowly go like that, and you'll start to notice the value becomes high, and then it becomes maximum. That's how you know you're perpendicular. So as a precaution to using Hall probe all the time, what do? You place the Hall probe and you rotate the Hall probe until what value is obtained? Maximum. And that maximum implies the fact that it's not perpendicular. Okay, so yeah, these are some of the things that we have. Now, equation derived probe. So tomorrow basic idea which of the Hall probe? It's a device that we use to find the magnetic flux density by finding the voltage across the wire. And when I mean across the wire, I mean laterally across the wire, not like over it. Okay. Now, how do we come up with the equation for it? Because we just said that it's directly proportional, right? There must be some evidence. So which I'm going to attempt to prove. What is it? No, it's random, but it's very important. Yeah. I mean, calibration is the first thing you do with any device. You buy any electronics, it needs to be calibrated. Even monitors, screens, colors, everything needs to be calibrated because they don't come out from factory as intended. So brightness, there's an option. They'll give you different colors. You can set the brightness and match it, right? Calibration is very common. No. It's to get the right colors. Okay, let's see this. How does this work? So if you have an electron here, let's try to understand what the electron is experiencing. So it turns out the electron that goes through here is actually going through straight, contrary to what I just said earlier. Earlier, I said that the electron actually bends which way? This way, right? But eventually, while investigating, we found the electrons actually try to bend that way, but they eventually go up straight. So the question is why? Close, but wouldn't that make some sort of deflection? We say it just keeps going straight. It attempts to go that way, but eventually it corrects itself. Particles. Yes, correct. So what's happening here is that it's a self-inflicted change. I'll explain what I mean by that. So this side becomes negative, right? Because the electrons are trying to go that way. And the other side becomes what? Positive, because electrons have left that place. Because of this, what happens is that you have a force that the magnetic field is applying. Which way? This way. This is the force due to what? Magnetic field. But now there's an electric field generated here, because plus and minus. And the electric field is applying force on the electron which way? The other direction. And they hit an equilibrium where both of these forces are equal, and as a consequence, your particle just goes straight through. We'll use that to come up with our answer. No, so I understand what you're trying to say. Some of them actually go there, and it creates a field to begin with. Because otherwise, if they come back to the center, it's like a feedback loop. This change causes that. So that's why it goes straight. Because if the change is not there, it will just go straight. Our repeat query, jara bujho nai, edike dekho, the electron goes this way. It creates a disparity between the two sides in terms of charge, which creates an electric field, which creates a reversal force there. But which force is still also available? The magnetic force. And they both equate. And eventually it starts to move like that. Okay. Now, so if I want to find the voltage here across the two terminals, let's give it a try. So can you tell me what is the formula for magnetic field? Force experienced by a charge in a magnetic field? F equals to? What is the formula for the force exerted by a charged particle in a magnetic field? It's not been 10 minutes. Yeah, BQV sin theta. What F equals to BIL? I'm charge not wire and conductor, right? So you have BQV sin theta. Sin theta likhlam na because it's 90, it's perpendicular. Can you tell me a formula? And this is going to be a proper check of whether you can retain any sort of information. What is the formula for the electric force experienced by a charge in the uniform field? Oh my goodness. Let me repeat my question. What is the value for the force experienced by a charge in a uniform electric field? Are you guys doing this intentionally? So what is it? What? EQ. I'll write this down. So what is the F in a uniform electric field? What? Huh? No. That's not wrong. But you're telling me the generic formula, which is E equals F by Q. I'm asking you, what is the formula for the force in a uniform field? Do you know uniform field exists? Yes. Eh? V by D to electric field strength. You guys are just randomly throwing around words. I don't think you understood the question. AJ, duita field erokom. And then there's a distance here D, and then there's a potential difference of V, and there's a charge inside Q, right? Yes. F by Q equals to V by D. So F is equal to VQ by D. So yeah, it just proves that you can't remember anything. Right, so that's going to be V. By the way, this V is what? Potential difference, okay? VQ by D. Now we need to set some parameters here. D hoche a value, the separation of the plates here, if you could say. V is going to be my what voltage here? the Hall voltage, because isn't the potential difference here the potential difference between the two plates, right? Q is the charge of an electron, B is the magnetic flux density, V is the speed at which the electron is flowing. Okay, that's important. We'll see in a minute why. So in this scenario, what should these two forces do? Equate. So if it is FB equals to FE, you get BQV equals to VQ by D, and the Q cancels out. So, sometimes students wonder, what if the wire didn't have electrons or it had ions in it? It doesn't matter. It'll have the same outcome because the charge value is not the consequence. Okay. Sometimes students will go like, oh, we took the electrons, but what if they're positive charges? No problem. It's just going to be the same thing because the charge has no consequence on your outcome. Okay. So ekan theke we get what here? The Hall voltage is equal to BD by DDV by V, just that much. Okay. So it took so far. So the Hall voltage V is equal to B into D into V. এখন we'll take one step further. Do you see that V there? That's the velocity at which an electron moves in a wire. Do you know what that is? You should, because it was in your AS. Yeah, the drift velocity. What's the formula for drift velocity? I equals to NA Q V. So V is equal to what? That velocity? I divided by NAQ. So if you can place query, you get B times D times I is I divided by NAQ. এখানে হচ্ছে এটা কি হবে? So A is going to be the water of this wire, the cross section, right? So cross section এর জন্য D into T, ওরা হচ্ছে thickness এর জন্য T use করে. So I can place that there. So I'll get B D I divided by N. A কি হবে? D into T times Q. And from there, we get this formula. VH equals to, D cancels out, BI divided by NTQ. The Hall voltage depends on these factors. Now, if I use a wire where the current is constant, charge carrier density is constant, thickness is constant, and the magnitude of charge is constant, what does the Hall voltage directly depend on? Right, that's how we know it. So, these will remain constant, by the way. There's no reason for your current to change because that's based on the supply. What is N? Charge carrier density. That is supposed to be constant because you're using the same material. Thickness of the wire must be constant. Charge must be constant. So eventually, this is directly proportional to that. Now, sometimes the Hall voltage is too small to register. Can you tell me what changes can I do to my setup so that the Hall voltage is higher? Yeah, you can use greater current. You can use a thinner wire, or you can use a material with larger charge carrier density or smaller charge carrier density. Smaller charge carrier density. Okay, so ওটা যদি ছোট হয় তাহলে এটা বেড়ে যাবে. Is that okay? And that is the formula. This is the derivation that you have in your syllabus. VH equals to BI divided by NTQ. Okay. I don't know. And there's no practical application of this because eventually, once you go to engineering, right, the Hall Pro has another version. Oita hocche much more advanced. It's basically a field meter, EM meter. এটা use করো না, এটা just ধরবাই করে not only B বলে দিবে, phi বলে দিবে, direction বলে দিবে, angle বলে দিবে, সবই বলে দিবে. So we are still like 50 years behind in our syllabus. Yeah, I mean, because যদি সব modern devices use করে, your syllabus would be like 3 chapters. So everything else is just right out there. কিছু করার নেই, it's all just available for you. Okay, so বুঝছো এটা? The Hall voltage and everything. Okay, so I'll explain. So first of all, let's try to understand the first force. So there's a magnetic flux provided here, and there's an electron entered. And as the electron enters, the electrons will start to move that way. But the wire has its natural electrons as well, right? Because the wire is delocalized electrons. So those electrons will also start to move that way. Because they're moving with the field provided. There's a potential difference from the top to the bottom, right? So what will happen is that the electrons start to move this way. And some electrons will go this way. And as some electrons go this side, this becomes more negative than before. And this will become more positive than before because the electrons have moved that way. So now you have negative field on this side and positive field on that side. Now the electrons that are coming in, right, they will try to go this way because of the magnetic field, but the electrons here that are already there will push it which way? The other way, because there's like a opposing electric field out there. And at one point, the numbers will start to move around until it stabilizes, where the magnetic force that they're experiencing and the electric force they're experiencing are the same. And as a consequence, the electrons will start to move at normal path again. And this opposing force comes from the fact that there is a potential difference generated here. Okay, because imagine this electric field wasn't there. All the electrons will just go and hit the side. Because it'll be a continuous flow of electrons, all of them will just start to go to the left-hand side. But eventually, because there's a buildup of electrons out there, it starts toward the incoming electrons, push them. And that more and more electrons start to come here, the more and more the push becomes. At one point, the subsequent electrons that are trying to come in can't go anymore, but they're trying. So it basically means that the magnetic force and the electric force are now equal, and they happen to just go straight. So initially, there has to be this thing show up, and then eventually it stabilizes and reaches equilibrium. That's when you get the voltage. So in a Hall probe, you'll notice the voltage goes from 0 to the value. It's not there right away. This buildup has to take place. It's very instant, but it does take place. It's just a way of representing current in equations. Yeah, that's why it's called convention. Huh? Because all the equations ever derived is based on current flowing from plus to minus, right? So why would we suddenly change it? Because it works. Everything is working right now based on the equation, right? Why change something that's not broken? Yeah. Conventional current জিনিসটা কি? So when you have a battery and a plus and a minus, right? Your current has to go somewhere. Now আমরা তো দেখতে পারি না. And think the year 1700, Benjamin Franklin, right? He's trying to figure out the key that's taken. There's something going around, right? So he assumed that there's some kind of energy passing through the wire, and he just went randomly plus to minus. Okay, that's what he did. Like that's what happened, and everyone started to follow for 250 years, and they worked on that idea, and everything worked, right? Lamps were working, bulbs were there, things were going normally until somebody discovered that the protons can't move anymore. It's the electrons that move around, and that means that plus to minus positive charge we imagine is not actually positive in charge. It's actually what in charge? Negative, which means it must be going the other way. But turns out, that the direction of current doesn't impact the energy it provides. So therefore, eventually, the energy is what we see, right? It doesn't make a difference there. That's why we even draw the diode the other way around, allowing which current to be passing through it, the conventional current. So electrons they কাজ করা হয় না unless we go into these kind of level deeper into it. আচ্ছা একটু এদিকে শুনে নাও, ক্লাস শেষ না, there's more time. I'll just show you এটা নোট একটা, so নোটটা একটু বলে নিয়ে কি দিব। এই যে একটু স্ক্রিনে, so this is the Hall probe. What is it? It's a circuit setup used to determine the magnetic field strength at a region. Okay, it's a circuit setup. The circuit consists of wire and a voltmeter connected across the wire at a point like this. That's how you connect your voltmeter. They'll ask you to draw this in the exam. তারপরে হচ্ছে as the wire is placed in the magnetic field, the charges in the wire deflect, and this causes a potential difference across it. The potential difference is directly proportional to the voltage. This is called the Hall voltage. Okay. To ensure that we get accurate readings, the wire in the field must be rotated until we get maximum value. This is to ensure that the charges are perpendicular to the magnetic field, the one I mentioned, right? And then this is the derivation. I mean, আমাদের যেটা করছি ওটাও add করে রাখবো, but derivation is basically that there's an electrostatic force and there's a magnetic force, and these two, try to balance out, and you eventually get this formula Bi divided by NGQ. Okay. And there's another question they ask you is that the magnetic force causes the electrons to deflect to the right, and the electrostatic force causes them to go to left. Eventually, the electrons attain an equilibrium and continue in a straight line. So they're trying to go this way and that way. Both of them are equal and opposite. So eventually, they just go to the center like that, balanced out. Okay? Because imagine electric field wasn't there. Where would all the electrons go? Yeah, they'll just go here and all the electrons will be stuck there. there will not be any current in the circuit. You still need them to flow through the circuit, right? To allow that to happen, there must be an opposite force out there. Naturally, it shows up because as the electrons start to build up here, the other electrons are now finding there's a force the other way, and they start to go that way. But when this force and that force become equal, they end up going straight. And that's what the current in the circuit is going to be on. No. So there is a potential difference. Otherwise, they can't be equal, right? So the electrons try to go that way, and then the magnetic field is taking them that way, and the electric field is taking them which way? The other way. And the fact that there's an electric field means there must be a what there? Voltage, right? That is the whole voltage. Okay, so we are almost done with the charges and magnetic field. Next class, we'll do something called a velocity selector. But tomorrow morning, class, it's going to be from 11 onwards. I'll solve a paper, okay? Just online. I'll solve a paper, a Bolicon paper, the most recent paper, 2024. No, October, I don't think it's out yet. May June, Judy Pawa Jai, I'll post it in Google Classroom. And I'll post which paper I'm going to solve. Oy paper we'll try to do one question from every topic we have as a recap. Okay, so yeah, okay, paper 4.